is. Hey guys, welcome again. So this is the second part of the DC-DC converter that's been controlled via MCU, where we will control the V out of the DC-DC converter using an MCU. So what we have done so far in part one, I really encourage you to go through part one first if you haven't done so, because if you come directly to this part, you might miss a lot actually. Okay, so what we have done is we take out all the unnecessary components that extra in our circuits. For example, the ender voltage here, the current controller, we don't need it, and also permanently make it run without ender voltage protection rubbish. Okay, and also we disconnected the what they call the constant current circuits, and also desolder all the component that's not needed, which is this or that one I'm mentioning now. Okay, so what we left with, let me check here. So we left with this circuit. If you remember, this is what we discussed previously. So we have take out this diode, take out all these components. This is for the constant current control circuit, so this one also be taken out. So we left only with this circuit, which is to control the voltage, okay, to control the V out. So the current practice is, if we want to change the voltage, okay, of the circuits, we need to manually control this potentiometer. Okay, we use a screwdriver to physically rotate this potentiometer to change the V out. Okay, what we want to do is we're using an MCU. Okay, we use an external MCU. Here is our friend, and we need to have some magic way of controlling the V out. Okay, so this is what we will work on. Okay, we will work on this magic way of controlling the output of this DC-DC converter from the MCU. But before we proceed to this feature, we need to understand the process of the DC-DC converter. So I come here to the datasheet of this LTC, what we are working on, but I can say it's this way, or this concept is working on all the other DC-DC converter or switch mode power supply, or SMPS. Okay, let me take screenshot of this guy here so we can highlight and comment on the circuits. Okay, cool. Make it big. So yeah, that's good. Let me choose bread. Okay, so from here we can see this is the voltage divider where we can control the V out. Okay, so this is the V out line. Okay, and we take one line from here, go to a voltage divider, and this voltage divider go all the way to a V out sense. Okay, the concept of this DC-DC converter, or all the SMPS, the switch mode power supply, is to the output of this V out sense. Okay, V out sense actually is connected to an internal op amp. Okay, this internal op amp got a reference of, if I'm not mistaken, in this case is 0.8 volt. Okay, so the internal op amp will do whatever it's need to do to keep this point, okay, equal to 0.8. If we go back to the data sheet and we search for the equivalent circuit, the LTC equivalent circuit should be somewhere here. Here we go. You see here what I'm referring to, the voltage divider that's go to the V out sense, and this voltage divider go to the V out. Okay, so it comes from the V out into the V out sense, and here it is, the V out sense. We got two comparators, one for the buck, one for boost, but either one, it's got the 0.8 volts. So this is the reference voltage of the DC-DC converter. So we can assume, let me change to blue. Okay, so we can assume the whole circuit or the whole this LTSC as a big fat op amp. Okay, as a big fat op amp with or converter with 0.8 volt. So now the op amp will do whatever need to do internally to keep these two inputs same. Okay, so for example, if the voltage here, let's say I apply, let's say 1 volt, I applied 1 volt here. Okay, if I apply 1 volt here, what the output will do, it will reduce the output. Actually, the output will be reduced. Why? To reduce this one, because if you remember, this one is connected through the voltage divider to the ground. Okay, and this one connected to here. So the output will be reduced to reduce this voltage equal to 1.8. Okay, guys? At the same time, if let's say I change this voltage to be, let's say, 0.1 volt. So what the op amp will do, it will increase, yes, I guess you guess it, it will be increase the output here. Okay, so this value here will be equal to 0.8 again. Okay, so when these two inputs become equal, let's say here 0.8 and here also 0.8, then the system will reach the balance condition and the output will be stable as it is. So this is how it works. Any disturbance to the balance condition, for sure this one will be a potentiometer. Okay, if you notice, let me minimize it. If you notice here, this is the potentiometer. This is a potentiometer that's come from the V out. Okay, so this is our V out. This is V out. Where is the one going again? Okay, so this is the V out. Okay, then got potentiometer here, and also we got the fixed resistor to the ground, which is here. So whatever disturbance happened to the system using this potentiometer, then the voltage over here will be disturbed. Then the op amp will do its job to maintain this point to, or bring it back to 0.8 volt again. Okay, so this is the standard practice, where we just use a potentiometer to disturb this this pin of what we call V out sense. So what we can do is we can use any source of voltage. Okay, this is voltage. Then we inject it to this point. Then with this we can successfully disturb the balance condition of these two inputs of the op amp and make the V out being changed according to the disturbance. Okay, whether we can inject higher voltage or a lower voltage to this point to make the V out go up or go low. Okay, but for sure not that straightforward. We need to have some proper circuit to do so. Okay, so now how we can get this what we call external voltage, since we want to use an MCU. Okay, that's good. So now the thing is, from where we can get this external voltage. So first we can use PWM signal. Okay, as you know, the PWM signal, if we filter them out, then we buffer it, we can pure DC voltage, then we can inject it to our system here. Okay, so this is the first thing, is use PWM. Second, use DAC, digital to analog converter. Okay, this one can directly output a pure DC voltage. Then again, this one we can inject it to our system as well. Or if we don't have these two, we can use a resistor multiplexer. Okay, let me jot down somewhere here. So this is the third. We use resistive multiplexer. How to do so? We just need to have a different resistors. Let's say here we have, with this resistor, maybe I have another resistor. Here also I have another resistor, and here another resistor, then etc. Let's say I have 10 resistors, then I need to add a multiplexer to the ground connected to these guys here. Then this multiplexer will be triggered to which resistor I want to connect, or can be connected multiple resistors to change again the voltage divider value, so it can be changed the V out as well. Or in the first way, we will disturb the balance condition, then we will affect the V out as well. Okay. Or the fourth method we can use is a digital potentiometer. Okay, digital potentiometer. So again, digital potentiometer is mean we just replace this guy here. Let me change to red. So we change this potentiometer with a digital potentiometer that's being controlled through the MCU. Okay, let's see here we have our MCU with a potentiometer. Then the MCU can send the put value, then in turn will change the or disturb the balance condition, which it will be change the voltage. Okay, so here we have four methods that can be used to control the V out of a DC-DC converter. Okay, so we will try to cover all of them hopefully in this series. I'm not sure if we cover all of them in this part or maybe in the next coming parts. Okay, but this is what we talk about. So maybe yeah, first I will talk about the PWM, then the rest will be, we'll cover it in the future. To prove our concept that when we inject a DC voltage at this point, the V out will be changed accordingly. For sure, we can't inject the DC voltage to here. We cannot directly do it, but we need to add a resistor before we injecting the DC voltage, okay, or on the way of the DC voltage. We delete this one. So we need to add a resistor at this point. Okay, then we can inject our DC voltage here, okay, to this resistor, because this one will act as another voltage divider. This one, the main voltage divider, this is the second loop of the voltage divider. Okay, and again, if we increase this voltage, okay, this point here will be increased as well, so the V out will be decreased. And at the same time, if we decrease this voltage, the V out will be increased. Okay, so for the time being, we will implement this circuit for testing and proof of concept of our claim just now. Then we can later we will replace this DC voltage with the PWM, DAC, or any other method of injecting a DC voltage to the network, okay, to change the balance condition of this node. So this is the latest circuit that we prepared in the first video. So what we can do is, if we go down here, let me increase this guy here. Okay, so we take, this is the point where connected to the Vout sense. Okay, so this point, it will go somewhere to the Vout sense of the LTC. So from here, I will add a resistor, then I will add or I will inject the DC voltage here. Okay, through the resistor. This resistor cannot be randomly chosen, need to be calculated for good results. Okay, but this one we will talk about it in the future. I'm not sure about in this video or the next video, but most probably in this video. Okay, we will learn how to choose the proper value of this resistor in our network.
Okay guys, so here's the demonstration of what we were talking just now. So here is our board, the modified one. Okay, here's the Arduino one. I use it as a power supply, okay, to inject voltage to the Vout sense that will disturb the balance system. Okay, now so as you can see here, this voltmeter will measure the voltage that output from this board, which is representing the voltage that's been injected to the Vout sense of the system. This voltmeter showing the output of this module, okay, the modified one. So what I'm injecting now, or before the injection, this one I already preset it using the Vout potentiometer, the Vout sense port. I set it to about 10 volts. Okay, you can see here it's outputting 10 volts. And from here I'm injecting 0.8 volt from this module to this one. I'm injecting 0.8 to the Vout sense. So now the system is in balance condition since I'm injecting 0.8. So this the preset of this module is still the same. So now we see what happened. What I will try to increase the injected voltage to the Vout sense. Okay, so now I will increase. Here we go, start to increase. You see now I injecting 0.81. You see the voltage is decreasing. There we go. You see? Now I injecting 1.1. The voltage decreased to 9.6 and etc. So if I go more, the voltage will go lower. The more I injecting, the lower the voltage will be. Okay, here we go. And by the way, the voltage we're injecting here is not directly to the Vout sense. The voltage actually go through this resistor. Okay, I don't have a fixed resistor, but I choose this potentiometer resistor. So later I will show you why I choose this potentiometer. Okay guys, so now we can control it using another external voltage that's been injected to the Vout sense through the resistor or R3. You see now, whenever I increase, the voltage will be dropped. If I go down again, if I decrease it, decrease the injected voltage, you see the voltage go up again. Here we go. When I go to 0.8 volts, go back to 10 volt again. So now let's see what's the point of this resistor. Let's say now 0.8 volts. If I go up, let's say to, for example, this one we represent, let's say we have a MCU with a PWM signal. So this PWM signal will be injected to the Vout sense. And as we know, the Vout for the PWM signal will be from 0 to 3.3 volt or from 0 to 5 volt. So let's say if from 0 to 5 volt, So if I go all the way to 5 volt here, representing an MCU with a 5 volt output, here we go. So this is a 5 volt output. So when I injecting 5 volt, the output will be around 5 volt also. So if I want to change this value, let's say I don't want it to be lower by 5 volt, maybe I want to change the value, let's say more than 5 or less than 5, so I can modify this resistor. You see, now I will change this resistor. You see, now the voltage is decreasing. Let's move back this again. This is where we control the V out. You see, now at the 5 volt, I want the V out to be, let's say, I want it to be, for example, 0.8 or 0 volt. Here we go. So around 0.8 volt, let's say. Here we go, 0.8. Okay, which is representing the 0 volt of the module. So at 5 volt, I turn off the module. Now if I go down again to 0, here we go, you see the voltage recovered again until the maximum of 10 volt will be reached when I hit the 0.8 volt again. Here we go. So 0.8 maximum will be 10 volt. Now when I go up to 5 volt, here we go, 3.3. So you see it's go down to 0 should be when I hit the 5 volt. Here we go, 0.8. Okay, so this is how we control it. We're injecting signal to the V out sense of the module to disturb the balance of the system. Okay, so this is just a very fast demo for you guys and very rough. Later we will learn how to calculate the resistor, how to replace this one with a PWM signal from a real MCU or ADC, or even what they call the digital potentiometer, the one we discussed in the previous part.
Okay guys, so here we come to the calculation part after we finish the demo, or the one we saw in the previous video. So let me open my pen. Well guys, let's have a look at the schematics first. Okay, so here is a schematic that I draw here. Okay, show exactly what we are doing. Okay, so here is our resistors R1 and R2. They already existed in the board, where R2, if I'm not mistaken, is 14K, and R1 is the variable resistor of, is it 500 if I'm not mistaken? I don't know, like I guess is a 500K. Anyway, so the thing we add on is this. Okay, this is the one we add on. So yeah, again, this one is already existed in the module. Okay, that's being connected to the V out sense. Okay, and the R1 connected between the V out of the module and the V out sense, and R2 connected between the V out sense and the ground. So the new resistor we add is R3, okay, where we will inject the voltage that I highlighted here as a VADJ, V adjust. Okay, so we inject this voltage to disturb the balance condition of this system and change the voltage of the V out accordingly. Okay, so here, in order to calculate these resistors, we have two equations to address, or two equations to work on, in order to help us to calculate and find the resistance we want to use. Because as we mentioned, these resistors, they are not randomly chosen, it must be calculated. So the first one, I took it from the data sheet. Okay, this is the data sheet of the LTC. Since we are using the LTC module, so just go and check the data sheet. Okay, so the V out is equal to 0.8. This is the Vref of the internal Vref of the LTC. Okay, multiplied by 1 plus the R2 divided by R1. This is from data sheet. Okay, you go and check the data sheet. This is new one that we drive it from the external voltage that added to the voltage divider. Okay, so the final V out, okay, the final V out after we apply the VADJ, so will be the V out that we calculated here, okay, minus R2 divided by R3, okay. This is the R3 that we add, the new one, which is here, multiplied by VADJ, which is the adjustment voltage, which is here, minus 0.8, which is the internal VRF again. Okay, so these are the two equations that help us to find all the necessary resistance for our work. Okay, so let's continue. I have prepared an example for you guys. Okay, so let's say I have these specs of my power supply. Okay, I want the V out to be 12 volt maximum. Okay, I can say this is the maximum, can be go up to 12 volts. And after I disturb the system, after I apply the adjustment, it will go down to 1 volt. So the final V out will be 1 volt. And by the way, let me go back. If you notice, guys, let me erase it. Eraser. Okay, where is the pen again? Here we go. So if you notice, this is the V out. Okay, so this quantity we calculated from here, from this equation. Anyway, so this V out, and this is the V adjustment. Okay, so if you notice, guys, when the V adjustment increase, what will happen to the final V out will be decrease. Okay, because we have a minus here. If we increase the V adjustment, the V out will be decreased. And at the same time, if we, can I change the color? Yep, there's blue. And at the same time, if we decrease the V adjustment, the final V out will be increased. Okay. All the others, like the V out here, all the resistance, the things, all will be fixed or maintained. It won't be affected anymore. It won't be have a role in our circuit. So only the VADJ will be the controller, okay, the signal that comes from the MCU or the DAC or PWM for whatever system. For now, I'll just assume there's an external voltage to disturb the system. If this signal go down, again, the V out final will go up. If the V adjustment go up, the V out will be opposite to it. So same goes to here. Okay, let me go back to the red. There we go. So that's why if you notice here, my V out, I set it to 12 volt. But the final V out, after I apply my adjustment, it will be reduced to 1 volt. Okay, because I'll apply 5 volt. Why I choose 5 volt for the VADJ? Because I assume I'm injecting this signal from the MCU, and the MCU, you know, most of the MCUs either will supply like 0 to 3.3 volt or 0 to 5 volt. And since we're using Arduino, so Arduino is able to supply 5 volts, so I will stick with the 5 volt. Okay, so the final V out is 1 volt. Maximum I want it to be 12, and the VADJ is a 5 volt. Okay, so this is the thing we need to consider at the early stage of the design. So now what we have R1 is already in the module, if you remember, is already there, which is 14K. R1 is 14K there already. And the V out, again, we just put it here in the spec. I want it to be 12 volts. So now I come to this equation. So I just need to calculate R2 from this equation. Okay. So I have R1 and V out already we mentioned 12 volts. So what else missing? Only this parameter is missing, so I can calculate R2. So after you do your calculation, then you will get R2 is about 200K. But with 200K, the V out won't be exactly 12 volt. It will be 12.2. So this is, we need to consider again. So now our voltage, for sure, you can get exactly what you need. It might be plus minus because of most of the resistors sometimes not exactly available in this as standard. Sometimes got the tolerance and all these things. So expect plus minus. So now our V out is being shifted to 12.2 volts. Okay, which is still okay. I'm okay. We still can control it using the ADJ later if you want, if you don't want it to go to 12.2 or want it to be maximum or 12 volt. Anyway, so now our R2 being calculated and the V out being shifted a bit up by 0.2 volts. Okay, let's continue. So let me change the ink to blue. Here we go. So now I want to calculate the rest of the circuit. I want to calculate the R3. So how I'm calculating R3, now we come to the second part of this calculation. So what do we have now? We have the V adjustment is a 5 volt, is given here. R2 is being calculated in this previous step. Okay, I put it here. V out, again, is given but is being disturbed. So it's been disturbed to 12.2 volt, and the final V out is being given also is a 1 volt. Okay, this parameter we need it in order to calculate R3 from this equation. Again, V out we have already with 12.2, R2 200K we have it already, V adjustment is a 5 volt given, and what left? Only R3. So we do our calculation, we do the math to this equation, and we will find R3 is about 64K. Okay, and again, the V out disturbed doesn't exactly give you what you want, but almost near enough. So the final V out being changed or disturbed to 0.9 volt, which is almost same what we need. Okay, so here we go. Very easy, simple, and straightforward calculation. We already calculated R2, calculated R3, and we set the V out and the V adjustment. R1 is already there. Okay, so that's good. That's good. So with these guys, I will move to the bench now, and I will try to set all the resistors, find all the resistors we need, and connect everything together, and we see how it's behave when we change the ADJ, the VADJ. Where is the pointer? So we will change the VADJ from 0 to 5 volt, and we see the behavior of the V out should be changed from here about 12 volts as 0.8, and as 5 volt this one will be go down to 1 volt as expected. Okay, so let's go to the bench, connect the circuits.
So now we will implement the circuit we discussed just now. Okay, so here is my power supply unit that will inject the signal to this guy, which is my target, to try control its output. Okay, let me move this one there. It's not connected yet. So here you see our target is here. Here is R3 and R2, the one we discussed just now, and R1 is already maintained the built-in SMD1, which is 14K. Okay. So now first of all I'll try to set R2 and R3 exactly same what we calculate in the previous parts. But sorry, I don't have the exact resistor, so that's why I will use this potentiometer. Each of them I believe is the 500K. So I will preset them with the help of the multimeter to the values we calculated. Okay, so we can do the testing. Okay, so I will start with R2. Okay, this R2 should be between the V out and the V out sense. Here we go. So now R2 is 200K. Let's go and check R3. Okay guys, so now we will adjust R3. This is R3. Okay, this R3 is between the adjustment voltage. Adjustment voltage should come from here in this green cable. Okay, and also we'll go all the way to the V out sense where they meet each other with the R2 and R1. I'll try to post the schematic for you guys. So how to measure this is we need one lead here on the green, and the other lead will be on the black, if I'm not mistaken. On the black of R2 should be somewhere here. Yep. Okay, so this one should be 64K. This one should be 64K. So I will try to adjust it to make it 64K. Oh, that's okay. Almost. Yep, 64K. So you done? 65. That's pretty easy. Okay, 64 looks good enough. So yeah guys, again, don't expect 100% mesh because the resistors I'm using, sorry, is just a potentiometer. So expect like plus minus few millivolts, or could be go to a volt because we already went in our calculation. There's about 0.2 volts offset. Okay, so now R3 done and R2 is done as well. Put it here. So now let's connect the power supply to the input of R3 and we try to test our circuit. Okay, so here is our setup after we already calculated and set R2 and R3. So here will be, as I said, the PSU that will inject the signal to our target. This is the target where we will control it. Okay, this multimeter will measure the output from the target. This multimeter will measure the output from the PSU, which is the ADJ. Okay, I use this as the ADJ adjustment to this guy. So let's power up and see how it works. For time being, by the way, I have him connect the output from the PSU to the ADJ. If you see the ADJ signal is here, that's connected to R3. There we go. Let me power these guys. So again, when we power up without the adjustment signal, this one measure the target. So the target is about 12.3 or 12.2, same what we calculated previously. And here is the signal from the PSU, which is the ADJ. So now I will connect this. Let me bring this down. Okay, say 3 volts. So now I'll connect the PSU signal to the ADJ, which is this guy here. Okay, I'll this. There we go. So now what we can see here. So I already connect the ADJ or adjustment voltage here from this PSU to the target, and also I rearrange the setup so you can see both of the multimeters while I'm changing the ADJ or the signal from the MCU. Okay. So first I'll try to sweep the signal from the PSU, which is representing the signal from the MCU or the PWM signal, DAC, or any other DC signals that will inject to the target to offset the V out. Okay. So now I will go down. You see, this is the ADJ. Now I will go down to 0.8. Here we go. So from our calculation, when the ADJ is 0.8, the V out is around 12.2. Here we have 12.3. Is okay because you know we use potentiometers for R2, R3, and also the resistors got some tolerances, and all the setups not that perfect, so we expect some offset. So that's why we see 12.3. Now I will go up for the ADJ. There we go. You see I'm increasing the ADJ. Now I reach 1.1. The output is decreasing. 12.2 now. I will continue up. There we go. You see I reach 3.4 and it's go down to 3.9. I will continue up. If you remember, we set our maximum to 5 volt, where this one will go down to almost like 0.9 volt or so. There we go. You can see I reach about 4.7, almost 5, and the output is 0.4. Okay, it's off already. So, which is exactly matching our calculation. We reach almost 5, the output go to about 0.4. Now I'll go down again. You notice the ADJ go down, the maximum Vout go up. Here we go. Sorry, this is not easy to be done on camera, but I'll try my best to do it okay. Here we go. The Vout recovered again. The Vout, the final Vout is already recovered when the ADJ go down to 0.8, and exactly actually when we go to 0.8, there will be no effect happen on the target because the system reached to the balance condition. Okay, guys. So again, this is how we can control the LTC or any DC-DC converter using external DC signal. So this one for sure is not shouldn't be from PSU or power supply, but could be from an MCU with a PWM, DAC, or digital potentiometer, or any other form of any form that can generate the DC voltage to be injected to our network. Okay, so we have learned how to do all the calculation and do the setup for it. Okay, so I'm going to release this video first because I can see it's kind of too long. So stay tuned for part 3, where we will talk about the PWM signal in details from the Arduino, and we see how to filter out the PWM signal and also how to buffer it and inject it to the our target. Okay, so in the next video I believe we won't use PSU anymore, okay, external this power supply, but we will use the Arduino itself directly to inject the signal to our LTC. So that's all for this video. I hope you have learned something new today. Happy learning, and see you soon in part 3.